Good morning or good afternoon, whatever it is for you guys. We're on the last notes of the year. Rolling motion. We're looking at rolling motion today for rotational motion day 6. And we're going to look at the notes here together, see if we can make sense of the whole thing. We got one practice problem to do. So let's see if we can find the notes here. There we go. All right. Rolling motion. And can we play those? Usually we can. Come on. There we go. Okay. So I think this is mostly review, so it'll go pretty quickly, but we've talked a little bit about how rolling motion is a combination, right? Because a wheel or a bowling ball or a ball is going to be moving forward with a velocity, and as it's moving though, it's rolling to facilitate the forward motion. So it's kind of two things happening at the same time, because you have a rotation and you also have like a straight line velocity. So if you look at the center of mass, which is one of the ways we look at objects, you can see that the center of mass is moving ahead in a normal, velocity v. But if you look at an outside edge, then it's going to be following a parabolic type of motion. So that motion is velocity-wise constant for the center, but on the outside edge, it's more complicated than that, because the wheel is rolling around that center and making contact with the ground and not slipping. It's important with rolling motion that it isn't slipping, so no peeling out or skidding your brakes. It has to be in contact with the ground in order for our physics to work. It gets a little more complicated if you're above the threshold of friction. So the equations, and I'll write these down on the board here, that we're looking at is the velocity of the forward motion, this isn't new, but is equal to the change in your distance over time. And for the rolling system, that means that it's 2 pi r, your radius, over that same time frame. Because if it goes through one revolution, it's gone one complete circumference of the circle. That's why we see the 2 pi r. So the delta x is equal to the 2 pi r. The distance that's traveled is equal to the circumference of the circle, okay? So what does that mean for the angular velocity? Well, 2 pi over t is actually equal to angular velocity. So we could also say the velocity of a rolling object is equal to the rotational velocity times r. Okay, rotational velocity or angular velocity is that w in the equation. So, and that's, again, it has to roll without slipping in order for that to be the case. So in terms of a rolling object, what's actually occurring here is it's motionless at the bottom. That's what we mean by not slipping. If you look at translationally, the object is moving ahead with a constant velocity. But rotational, the aspect of rotational, the top edge is rolling forward and the bottom edge is rolling back. So you have a positive angular velocity and a negative angular velocity because of the directions they're going. When you add that up together to describe the rolling motion, which again is taking into account a combination of translational and rotational, what you see is the top edge is moving ahead with 2 times the velocity. the center is still moving ahead with normal velocity, and the bottom actually is motionless. The very bottom that's at contact with the ground is instantaneously at rest. Okay, so that's the idea behind the rolling without slipping. So you take the translational, which is, you know, our normal linear system. It's moving ahead with the velocity. You add the rotational aspect where the top is moving ahead, but the bottom is moving backwards. So it's positive versus negative. And you add them together and you get the top edge is rolling ahead with double the velocity, bottom edge is motionless, and the middle is moving ahead at a constant speed. Okay, so let's take a look at the problem together. We're gonna go on a 60-mile road trip to get toilet paper in New Hampshire or wherever they have it at 45 miles an hour. And we wanna know, firstly, what the tire's angular speed is, and secondly, how many times did the tires, you know, revolve during this 60-mile trip. A couple things we need to know. The radius, oh, that's diameter, whoops. Let me just change that. The diameter of your tire is 0.6 meters, and the trip is 60 miles, and you're going at a good conservative 45 miles an hour must be your average speed. And let's calculate this. Of course, you're driving a Jeep. Here, just picture yourself on a day, not like today where it's sunny outside, you can drive around with the top off your Jeep, and you have a diameter of your tire of 0.6 meters. We know you're traveling at an average speed of 45 miles per hour, and you're going a distance of 60 miles. All right, so first thing that you need to know in order to find the angular speed is to figure out what your speed actually is in meters per second, okay? So you're traveling at 45 miles an hour. Which could be written out as miles over hours. And because we want this to be in meters per second, we know that 1 miles per hour is equal to 0.447 meters per second, or you're traveling at around 20 meters per second. This is a combined conversion because it's already got the miles and the hours built into it to convert right to meters per second. So that's kind of a nice shortcut if you have to do a lot of these here. So the Jeep is moving at 20 meters per second. And we know that looking at the equation we wrote down, that your velocity is equal to rotational speed times r, okay? Now, for this problem, your radius is half of this. So 0.6 meters divided by 2 gives us 0.3 meters is your r. And that's the r here. We are looking for w, and we know velocity. We just found velocity is 20 meters per second. So let's set the equation equal to angular velocity, and that's going to be v divided by r. So our velocity is 20 meters per second, and our r is 0.3 meters. So that gives us an angular velocity of 67 radians per second. Okay, so that's your angular speed of the tire. That's telling you how quickly the tire is rotating. It's going 67 radians per second. Okay, that's not revolutions per second. That's radians per second. And we're going to use that for part B, because for part B we want to know how many revolutions that is for the tire. Okay, now in order to figure out revolutions, we need to know time. So the easiest way probably to find time for this is to use miles per hour and miles, because we do know both of those quantities pretty well. If you remember, your change in time is really equal to the distance you've traveled and the velocity that you're traveling at. Okay, we have that kinematic equation up here somewhere. This one here. Oh, you can't see that. Boopity boopity boop. There we go. Velocity is equal to delta t, delta x over t. I've moved stuff around a little bit, but same idea. So the distance we're traveling was 60 miles, and the velocity was 45 miles per hour. All right, so you can see miles is going to cancel out. Hours is going to be our unit, so we'll know how long this trip takes in hours, and then we can convert that to seconds. In 1 hour, we actually want seconds, right? So in 1 hour, there's 3,600 seconds. So in 1.33 hours, we're talking about 4,800 seconds. Okay, so that's how long the trip will take in seconds. Of course, you're driving a Jeep in the sunshine, so you might want to take the long way. All right, so how many turns is that? So we know that you have 67 radians per second, and now we know how long a duration is, so we can figure out for each turn of the wheel how many radians we're traveling. So one of the things we have to figure out first is our total angle, right? So we know that it's 48,000 seconds, and we already calculated our W over here at 67 radians. So if we're traveling at 67 radians per second, we can multiply that by the 48,000 seconds, 4,800 seconds, sorry, 4,800 seconds. And we see that we have moved 3.2 times 10 to the 5th radians total for that trip. Okay, so that's how many radians we've covered in that 60-mile journey at 45 miles an hour. Okay, so that's your total angle. That's your total radians. That doesn't tell us revolutions, though. That just tells us radians. So how do you convert out of that? Well, if you take your total delta and you convert that with 2 pi radians, that will tell you your revolutions. That's how you convert from one system to another. If you remember, 2 pi is a complete circle. 2 pi radians is a complete circle. So if you take your 3.2 times 10 to the 5th radians, and you divide by 2 pi radians, radians will cancel out, and we're just equal to the amount of revolutions. There it is. So your tire has rotated 51,000 times in that journey. Okay, so 51,000 times is the amount of time your tire revolves in a 60-mile journey at 45 miles an hour. That's a lot of revolutions. And of course, each tire is, you know, rotating that much. So that's a big part of the wear and tear with wheels, is that they have to rotate so much for each trip that you take. Okay. Now remember, this is how many revolutions it would take regardless of your speed. You know, the speed doesn't really come into this calculation. You have a certain distance that you have to go. And, you know, if you go faster, the revolutions are going to be faster, but this is how many revolutions it takes total. So along with this section, you have 2 homework questions. I'm not sure why it goes backwards, because it's question 16 and question 13 on page 218, 219. But try those out. We can talk about those when we come back together. And yeah, so hopefully those notes make sense. Last notes of AP physics here. And so now we're going to move on to just reviewing. Thanks.